So the handout that I've included is mostly just technical details. I've tried to make sure that the presentation itself is as minimally technical as I can and focus more on the conceptual stuff. But if you're curious about the nitty-gritty math details, you can have a look at the handout. So I'll be talking about logic-governed worlds and their applications. What exactly are logic-governed worlds? Well, I'll get to the details, but essentially, I'm trying to come up with some account of worlds, possible or impossible, that allows us to be very flexible about what logical laws hold at these worlds in order to model certain claims about some modal claims about logics that kind of show up in the literature sometimes. So just a little roadmap as to where we'll be going. First, I will give a very brief and very selective history of possible and impossible worlds leading up to this project. I'll talk a little bit about why kind of existing accounts of impossible worlds don't really do the job. They can't really capture accurately certain modal claims about logics and why we need a new type of framework. Then I'll offer a framework, not necessarily the best framework, but just one that works. And then I'll discuss some applications. And finally conclude on a brief objection as to why my framework might be problematic in certain respects. So, as many of you will be aware, possible worlds were introduced way back by Saul Kripke to provide semantics for certain systems of modal logics. Traditionally, possible worlds are complete and consistent descriptions of how the world might be, and they're incredibly useful for providing truth conditions for modal claims. In particular, necessity and possibility operators are characterized by possible worlds. So we have box P is true at some possible world W, if and only if P is true at every world possible from the perspective of W. Standard language is that W can see these other worlds, or these other worlds are accessible from W. Possibly P, diamond P is true at a world, just in case P is true at some world that's possible from the perspective of W. And to just give a quick example, so here we have a small model with two worlds. At world 1, P is false, or P is some arbitrary proposition. At world P is true. World 1 and world 2 can both see each other. World 2 can see itself, but world 1 can't. And this means that at world 1, every world that it can see satisfies P. So W2 is the only world that W1 can see. So that means that necessarily P is true at world 1, but not at world 2, because there's a world that W2 can see, namely W1, at which P is false. But possibly P is true at both worlds, because both worlds have some accessible world, namely W2, at which P is true. And so this has applications not just for dealing with ordinary alethic modalities, but also the box operator and the diamond operator, assuming they're interchangeable, can be interpreted in epistemic, doxastic, deontic ways, and various other ones. And some of these interpretations, well, upon interpreting them this way, people realize that that there are problems. In particular, the structure of possible worlds, how they're set up, means that they only really care about material equivalence. They don't really distinguish between the meaning of different sentences at worlds. And that gives rise to various problems when modeling, in particular, hyperintentional phenomenon. So just an example, classically speaking, 2 plus 2 is equivalent to Fermat's last theorem. Fermat's last theorem is vastly more difficult to prove than 2 plus 2 equals 4. And prior to the 1990s, people didn't know if Fermat's last theorem is true. But if we interpret the box operator as an epistemic operator, then we get this result that an agent would know 2 plus 2 equals 4 if and only if they know Fermat's last theorem. But that obviously was not the case before the 1990s, and intuitively still isn't the case, even though both are true, simply because they have different content. Just because you know one doesn't necessarily mean you know the other. So what do we do about this? Well, enter impossible worlds. There are many other accounts of impossible worlds other than the one by Berto and Jago that I cited. I just list this one because their recent book is pretty comprehensive and gives a nice account of them. Nothing is at stake on, nothing hinges in this talk about using this particular account of impossible worlds. It's just a good reference. So the way that impossible worlds solve these certain hyperintentional problems is that we can basically do whatever we want at impossible worlds. They have a lot more flexibility than ordinary possible worlds. Exactly how much flexibility depends on the account. In kind of the most extreme examples, we can assign whatever truth values we want to whatever formulas we want at impossible worlds. And that allows us to do things like make logical truths false at impossible worlds. So just take this Fermat's last theorem example. Suppose we have at the actual world 2 + 2 = 4. That's obviously true. And suppose at this impossible world, accessible from the actual world, we also make 2 + 2 = 4. But suppose at this impossible world, we just assign the value false to Fermat's last theorem. And because we can do this, they have this type of flexible structure. And because this impossible world is accessible from the actual world, this means that although we know that Fermat's last theorem is true, that 2 + 2 = 4 is true because it's true at all accessible worlds, we don't know that Fermat's last theorem is true, or at least some agent potentially might not know, because there's this accessible impossible world at which Fermat's last theorem is false. So the story goes that impossible worlds have all kinds of great benefits. They solve these problems. Awesome, fantastic. But it's not quite the end of the story, because there are certain types of claims that are quite difficult to model with impossible worlds, and these are certain claims about modality. Claims about logics involving modalities. So this particular one that I list probably can be captured with impossible worlds, but others can't. And this one's just kind of a good illustration of counterlogicals, because a lot of these claims involve counterlogicals of some kind. So here's a sample statement. If Saul Kripke were both human and non-human, he would have won the 2000 election. Well, classically, any contradiction implies any statement. So we can't make the sentence false in any possible world that's kind of governed by classical logics, even though it intuitively seems false. Presumably, Kripke would not have won the 2000 election, regardless of his humanist status. And so we need to be able to express humanist and non-humanist simultaneously at a world. Impossible worlds can deal with that, but not other issues. So, for example, if intuitionistic logic were the correct logic, then the continuum hypothesis would be true or it would not be true. So, in intuitionistic logic, obviously it's it's a paracomplete logic. So you can have statements that are neither true nor not true in that logic. And as far as I remember, in intuitionistic ZF, the continuum hypothesis is independent of intuitionistic ZF, I think. But even if it's not, we still are unable to model this particular statement using impossible worlds, because impossible worlds don't really have the right structure that allow us to express the antecedent with the kind of precision we need to. Similarly, if classical logic were the correct logic, it would be impossible to validly infer everything from a contradiction. To express this within some sort of modal framework, we need to have worlds that are governed by classical logic in the antecedent, and we need to express this modal claim and the consequent, that it's impossible to validly infer everything from a contradiction. And in order to do all this, we need different worlds that are governed by different logical principles. And that's really the crux of the issue. Existing accounts of impossible worlds don't really have the right kind of structure, or at least existing accounts that I'm aware of do not have the right kind of structure to capture these kind of statements. Most logical laws at impossible worlds are either non-existent in the sense that we can just assign whatever values we want to whatever formulas we want, or else the properties of logical connectives are sort of global in the sense that are defined for all possible worlds. And additionally, there's no way to really express the local validity or invalidity of formulas at a world. If we want to have worlds that are, say, governed by a particular logic, we want to be able to express that certain formulas are kind of valid inferences of that logic at that world. And so we need kind of additional languages or additional operators or predicates or something to be able to express this. So, well, yes, that's what we need. And that's what I'm trying to do. So with that problem kind of established, we can start working towards a solution. So the first question that we need to ask is, what should worlds be? Sort of metaphysically speaking, my inclination is to avoid metaphysical commitments with respect to these worlds as much as possible, not just because of any kind of general inclination to avoid metaphysical commitments, but also because we are going to need to deal and accommodate some very wacky logics, including, say, the trivial logic. We're going to need to have worlds governed by the trivial logic. And so if we want to do that, at least I generally do not want much metaphysical commitments to such worlds. So the approach I take is just sort of a set theoretic approach, where I treat worlds as these sort of ersatz, some kind of ersatz world, and they'll be set theoretic constructions with different components, each containing formulas. So there'll be 5 tuples where each element is a set of formulas. The next question is what meta theory we should use. So I'm going to be talking about all these kinds of logics. What would be the appropriate logic to use in the meta theory? And the selection here perhaps might seem to threaten the project, because if you say, oh, well, if you're making some sort of commitment to a logic in the meta theory, well, that sort of defeats the purpose of the whole point. But we need to make some commitment of some sort. So I just kind of work within some classical background set theory. But this is for sociological reasons, not philosophical reasons or kind of technical reasons. Everybody's familiar with classical set theory, and by everybody, I mean logicians. And so it's kind of a nice common ground. It's not necessary. If we wanted to develop this account of worlds within certain non-classical set theories, we can do that. And the resulting differences would largely be a difference in how we characterize the semantics theoretically. So next, we need to consider what formal languages we're using. We want to talk about different logics, and in order to do that, we need to kind of have some sort of fixed set language in which formulas of these logics can be expressed. So I call this just this base language. And we also need to talk about inferences of formulas of that base language. So for example, we could have some sort of propositional language containing like P, not P, conjunction, disjunction. Then we need to have inferences, which I represent with this little arrow. And for inferences, I kind of have them relate a set of formulas to a single formula. If we wanted to have kind of multiple succedent inferences, we could. That's just a kind of a personal choice because it seems simpler in this case. And it's worth noting that the base language here doesn't have to be propositional. It can be first order, it could be a language of sequence, some generalization of sequence. And having that flexibility with the base language allows us to kind of have worlds closed under different logics. So you can get, say, certain logics that are characterized by some proof theory, some sequent calculus that you can't really characterize through some, say, a Hilbert system. So having that flexibility allows us to kind of capture different logics if we would like. And it's worth briefly digressing about whether we need to include meta-inferences in this discussion, or meta-meta-inferences, meta-meta-meta-inferences, however high you want to go in these hierarchies. The past couple of years, there's been a fair bit of literature talking about how high up this kind of hierarchy of meta-inferences we need to go in order to distinguish between very similar logics. And the answer I take here is that if we want to include all of these big meta-meta inferences, or even just normal meta inferences, we can. But whether we choose to do it or not is largely just a matter of what convenience or what you need the system for. So if you need to distinguish between classical logic and ST, for example, then you could add meta inferences to the normal inferences and include them as well. But for the sake of this presentation, I'll just focus on having some sort of base language and inferences about formulas of that base language. So that is the formulas of logics. Then we have another language on top of that, including 3 operators, which are intuitively a validity operator, V, an invalidity operator, I, and a contingent fact operator, F. So these are supposed to be read that phi is valid, phi is invalid, phi is a contingent fact, and these can be true or false at a world. What the truth conditions of these operators are, I'll get to in a moment, but at the moment, it's just worth noting that these are not validity predicates in the sense that you might think of a validity predicate in truth theory or something. That this is not that. This is something much more kind of general and flexible, and it's not. There's no kind of definable self-reference or definable validity predicate through self-reference in the kind that we get in truth theory. This is something else entirely. And I'll get to the semantics for those in a moment. But quickly, before we do, we should consider what aspects of logic should be included. And this is related to the kind of discussion about, do we need to include meta inferences? So we can't just talk about theorems of a logic, and we can't just talk about the inferences of a logic, because they can coincide but differ at some higher level. In the meta-inference literature, it's being kind of noted that we also need to include either the invalidities or perhaps anti-validities of logics in order to distinguish them correctly. Anti-validities are, you can think of them as a generalization of a contradiction or a statement that is never true, never satisfied by a particular logic. So contradictions are classical anti-validities, but they are not anti-validities in, well, most power-consistent logics. LP has no anti-validities, but some other power-consistent logics do. What I'll do is that I'll include discussion of theorems, valid inferences, and invalid formulas and inferences. This decision is largely for simplicity, because that's kind of the bare minimum we need. We can include discussion of anti-validities if we want, and we would add an anti-validity operator. So we had the validity, invalidity, and contingent fact operators. We could add an anti-validity one if we want to say that a formula is anti-valid at a world. But I'll just kind of avoid that in this talk just for the sake of simplicity. Okay, with all that out of the way, we can actually get to what worlds are. So I take worlds to be a 5-tuple containing 5 collections of formulas. We have a set containing all of the non-logical, or you could call them contingent facts that hold at a world. We have the collection of all formulas that are considered valid at that world. These could be considered like the logical theorems of that world. Then we have the collection of all formulas that are invalid at the world. These are not necessarily those that are anti-valid, but it could include just things like, P, Q, P or R, those type of things. Then we have the collection of all inferences that are valid at a world. So you might have a world at which modus ponens is valid, and you have the collection of all inferences that are invalid at a world. For some logics, modus ponens is not valid, and so depending on which world you're considering, different inferences would fall under different collections. So now we can actually get to the truth conditions. A formula or an inference is true at a world W, just in case it is a contingent fact or logically valid at that world. And here we can kind of see that these validity operators are not validity predicates. Since a formula is considered valid at a world, just in case it's contained in one of these validity sets. And phi is not true otherwise. And we can define the operators themselves. So v phi is true, just in case phi is valid at W, namely if phi is in one of these validity sets. F phi is true, just in case it's contained in a set of contingent facts at that world, and phi is invalid, just in case it's contained in one of the sets of invalidities. Yeah, and so that's the general setup. And as it stands, things are incredibly well flexible. As you can probably tell, at the moment, we can just sort of define whatever we want. We can define whatever validities we want at whatever worlds. You might think that's kind of too flexible, since I was critiquing impossible worlds about the same thing. But we can impose some extra conditions that make this more strict. So some of these conditions are as follows. So we could require that every formula or inference at a world is valid or invalid. This is sort of an analog to the law of excluded middle. We could require that no formula is both valid and invalid. This is sort of analogous to a law of non-contradiction. And depending on what logics you're dealing with, these additional restrictions might not be appropriate to impose. So you might have, say, certain paraconsistent logics where it has a formula that's both valid and invalid. For example, if you have some paraconsistent logic that has a truth predicate, and the liar sentence is a theorem of that system, the liar sentence might be both valid and invalid. And another criteria we can pose is the sort of closure condition, so that if an inference rule holds at some world and all of the antecedent conditions of that inference hold at the world, then the consequent holds at that world. There's a similar condition about closure, but for validity. So if an inference is valid at a world and all the antecedent conditions are also valid, then the consequent is also valid. We could impose that the set of contingent facts only contains atomic formulas to prevent us from just randomly making things true at worlds. And finally, we could suppose that worlds are closed under uniform substitution, so that if some formula is valid at a world and psi is some uniform substitution of that formula, then psi is also valid. So these are supplemental conditions that we can impose on worlds. I don't particularly like exclusion, but some of the other ones I think are pretty important. The closure conditions and substitution in particular are incredibly helpful for a wide range of reasons. So I'll be assuming them going forward. So with that description of worlds kind of set out, we can start looking at what we can do with these worlds. So the first thing we can do is provide semantics for counterlogicals and various counterlogical type claims. And we can do that by simply using the standard ordinary semantics for counterfactuals. So going back to Lewis, David Lewis, that is, a counterfactual is true. If phi were the case, then psi would be the case, is true at W. Just in case, psi is true at all of the worlds appropriately similar to W, at which phi is true. The appropriately similar aspect is just being some sort of accessibility relation. And counterlogicals in this framework can be defined in a very similar way, but instead of just having one antecedent formula, I'm allowing there to be a collection of antecedent formulas. And the reason for this is because we need to allow for formulas like if classical logic were the correct logic. And classical logic contains more than one formula, presumably. And other logics similarly. So we need to have the antecedent of counterlogicals contain more than one formula. But the truth conditions are just the same. And the antecedent conditions can contain expressions about validities, invalidities, and contingent facts, as well as just ordinary base formulas or inferences. So just to come back to the examples I gave earlier, we have this one. If Saul Kripke were both human and non-human, he would have won the 2000 election. If we let K mean Saul Kripke is human and E mean Saul Kripke won the 2000 election, we can suppose we have this model and use this as a counter model to show that the counterfactual is false. We can have an actual world that, suppose, for the sake of argument, satisfies the law of explosion. We have a paraconsistent world accessible from the actual world that is, paraconsistent. And suppose that at the actual world, Saul Kripke is not both human and non-human, but at the paraconsistent world he is. And suppose at this paraconsistent world, he did not win the 2000 election. And because this paraconsistent world is accessible from the actual world, that allows us to make it false at the actual world that Saul Kripke, that will make this counterlogical false, that if Saul Kripke was both human and non-human, he would have won the 2000 election. We can move on to the other two slightly more complicated examples. If intuitionistic logic were the correct logic, then the continuum hypothesis would be true or it would not be true. So to model this, let I be just some set of axioms for intuitionistic logic. It can be just any old, preferably, at least because we're working within a propositional framework here, or at least I'm assuming a propositional base language for the sake of this presentation, it could just be axioms from a Hilbert system. And let C be the continuum hypothesis. Again, if we wanted, we could kind of have the base language be some first order language and actually express the continuum hypothesis properly. But for the sake of simplicity, let's just let the letter C be the continuum hypothesis. Suppose we have this intuitionistic world, and we can not just stipulate that it's intuitionistic, but we can make it intuitionistic by imposing these conditions on it. So we stipulate that for each axiom A in this axiomatization, A is valid at that intuitionistic world, namely each such axiom is contained in the set of valid formulas at that world. And suppose that modus ponens is valid at that world too. Modus ponens is contained in the set of valid inferences. And together, because I'm assuming that I'm assuming the closure conditions, the additional closure conditions I talked about, this entails that every theorem of intuitionistic logic is valid at this world. Thereby, this world is an intuitionistic world. And suppose that at this world, the continuum hypothesis is neither true nor not true. And because this intuitionistic world is accessible from the actual world, we can make this counterlogical false. at the actual world, where this collection of antecedent formulas is just an axiomatization of intuitionistic logic, plus the expression that the claim that modus ponens is valid, and the consequent is just C or not C. And it doesn't matter if the actual world is intuitionistic or not. What matters is that there is an accessible intuitionistic world that can make this false. And so finally, moving on to the last example of counterlogicals. If classical logic were correct, it would be impossible to validly infer everything from a contradiction. So let C just be a set of axioms for classical logic. Again, given the context, we can just assume it's some Hilbert-style axiomatization. Suppose there's some paraconsistent world accessible from the actual world. And suppose that for each classical axiom, it's valid at the actual world. Modus ponens is valid at the actual world. Again, I'm just assuming this for the sake of example. And because we make these assumptions, this entails that the actual world is correct at the classical world, that the actual world is classical. Now, because the actual world can see itself, that means the principle of explosion is possible at the actual world. And which means that it's not possible that explosion is a false claim at the actual world, which can make this entire counterfactual false. We have an axiomatization of classical logic in the antecedent, and this claim that it's impossible to validly infer everything from a contradiction in the consequent. As I think about it in this example, we don't even need the paraconsistent world. We can just like have the actual world on its own. So sorry about that. But yeah, regardless, we can still express the claim. We can provide counter models for the false claims, but yeah, we don't need this paraconsistent world. So that is one application. We can express counterlogicals and formulas like counterlogicals within this framework, but we can do a lot more. And this other stuff is actually why I originally started developing this type of framework, is that we can express claims about the knowledge and belief about logic within this framework. So recall that the box operator can be interpreted epistemically and doxastically. And that is true both in traditional modal logic and in the present context. And in doxastic logic, we have certain other kinds of modalities and operators. Most notably, we have the conditional belief operator, where you can express things like, I believe that we'll have to move to online teaching again if there's an Omicron outbreak. I live in New Zealand. We do not yet have a big Omicron outbreak. Everyone's kind of expecting it to happen. Hopefully it doesn't. And we can also have dynamic operators, which change the model, essentially. And this particular one it's called a public announcement operator. So we could say something like announcing an Omicron outbreak, say if the government announced it, it would result in us moving to online teaching again. Now, how does this have bearing on the present context? Well, we can express claims of knowledge and belief about logics, which occurs quite frequently, or at least it seems to, among people I'm around. People might express a belief that some logical inference is valid or not valid, and then change their mind about it later. And that is a kind of belief revision, but it's a kind of belief revision that's very difficult to model formally. And so this particular framework gives us a way to model that type of belief revision. So like with counterlogicals, we need to have the set of conditions for conditional belief be a set of formulas, because we want to say things like, I might believe the law of excluded middle is correct, conditional upon classical logic being correct. So we need this whole collection of formulas to be conditions. And similarly, we might want to have update operators that update by sets of formulas. We could update by entire logics and change the model to delete certain worlds that have certain logical properties. So just to give some examples, we can say things like, I know that contradictions are invalid. We could say things like, I believe that modus ponens is valid. We could have even much more complicated things, like I believe that disjunctive syllogism is valid if conditionals are material and modus ponens is valid. So depending, like, I think given the assumptions that I've made about closure and substitution holding to worlds, I think this is actually a theorem of that class of worlds. We can also have other things like this is an example of update. If you announced that the law of excluded middle was valid after that announcement, it might be the case that double negational elimination is true. Now, this is not a theorem of the framework because you can have other worlds that might not be the case. And we can have this giant complicated one, which is quite fun. This says that after announcing that classical logic is correct, the law of excluded middle would be valid. In this update operator, I've just included a brief axiomatization of classical logic. Has 3 axioms and modus ponens. By updating and assuming that they're all valid, we delete all of the worlds in the model at which they're not valid, and what is remaining is only classical worlds, and thereby law of excluded middle is valid. Oh, sorry, there should be parentheses around this last law of excluded middle here. But yeah, this is a theorem of the class of models I'm considering. And those are the 2 main applications I want to talk about. I'm sure there is plenty more, plenty other ways to adapt kind of traditional modalities or operators to allow them to express claims about logics. So I'd like to just conclude on one objection, that perhaps this framework is too powerful. You can certainly do a lot with it, and you might worry that maybe it's too expressive, and that expressivity kind of causes problems. A reply I have is that, well, it actually can be axiomatized. I provide an axiomatization in the handout and demonstrate how we can extend that axiomatization to include various modal operators and update operators. The objection in response to this reply is that, well, the axiomatization I provided requires uncountably long conjunctions. And that's not the most desirable property you would want of a proof system. And this is the point where I'm kind of a bit stuck. So I have 2 potential replies in response to this one. The first is that if we restrict the modal languages to, instead of, I made a big deal about how we need to allow updating by sets of formulas, have sets of formulas as conditions for conditional belief, etc. If we restricted that to only allow for single formulas, then we could get a finite axiomatization that doesn't involve giant, uncountably long conjunctions or even countably infinite conjunctions. It would all be finite. However, we would lose some expressivity by doing that. Now, we would still be able to express certain important things, like if we have a logic, say, for example, classical logic can have 3 axioms plus modus ponens. If we assume uniform substitution, then we can get all of classical logic from just those 4 things. So we can still get certain logics, but if we want logics that are not necessarily closed under uniform substitution, then we would lose those by making this restriction, which you might not be too concerned about, but it's something to note. The second potential reply is that there are some index sequent calculi that I'm working on that seem promising, but I don't actually know if they work. And I have not yet sorted them out well enough to claim that I believe they work. I'm still not sure. So that's where I'm at now with this project. It seems like, well, there's still plenty left to do, but that's where it is so far. Thanks for listening.